Let me ask you something. What happens to your homestead the second the grid goes down? Everything stops. The freezer full of meat you spend the whole summer filling, the pump that pulls water from your well, the LED strips in the chicken coop keeping your hens laying through the dark months, the radio you depend on for weather, the phone charging on the counter, all of it, dead, gone. Because you are, like most people in this country, completely and totally dependent on a cord you don't control, running from a utility company you've never met to a breaker box in your home that you assume will keep doing what it's always done. And most of the time it does, until it doesn't. Now, I'm not here to scare you. You already know this. You felt it that week the ice storm came through, or when the substation 3 counties over blew a transformer and your county sat in the dark for 4 days while the crew worked overtime. You already understand at a gut level that dependence on centralized power is a vulnerability. That's probably why you're here. But here's what I want to talk about today, and I want you to stay with me on this because it's going to sound strange before it sounds brilliant. The ground beneath your feet is already producing electricity right now, under your garden, under your pasture, under the mulched beds you put in last spring. There is a quiet, continuous, slow electrochemical process happening inside the soil that has been powering devices for over 150 years. And almost nobody talks about it anymore, because nobody can charge you a monthly bill for it. Today, I'm going to show you how to build what's called an earth battery, not a solar panel, not a wind turbine, not a propane generator that guzzles $6 an hour. A battery that you bury in the ground, that costs you $39 in materials if you shop smart, that has no moving parts, produces no noise, requires no fuel, and that will sit quietly in your soil, generating usable low-voltage DC electricity for months, potentially years, without you touching it again. Now, before you click away thinking I've lost my mind, I want you to hold on, because this isn't fringe nonsense. This isn't perpetual motion mythology. This is documented, peer-reviewed, 19th century electrical engineering that was used to power real telegraph networks across continents before it was quietly replaced by something that cost more, required infrastructure, and created a customer base that pays a bill every single month. That's not a conspiracy. That's a business model, and we're going to walk right around it. Let's talk about what the off-grid power industry is actually selling you and what it's costing you. A decent entry-level solar setup for a homestead, not a whole home system. Just enough to keep some lights on, charge devices, run a small refrigerator. You're looking at somewhere between $3,000 and $8,000 installed, depending on your location, your roof, your inverter, your battery bank, and who's doing the work. If you go lithium iron phosphate batteries for storage, which are the current recommended chemistry, you're adding another $1,500 to $4,000 on top of that. And those batteries degrade. They don't last forever. In 10 years, you're replacing them. Small wind turbines for residential use, forget it. The maintenance cost on a residential wind turbine, the bearing replacements, the blade inspections, the inverter failures, will eat your savings inside of a decade on most installations. The industry knows this. They just don't lead with it. Propane and diesel generators. I don't need to tell you what fuel costs right now. And generators require oil changes, air filter replacements, carburetor cleaning, spark plug cycles, and they fail exactly when you need them most, because that's what mechanical systems do. Now, I'm not anti-solar. A well-designed solar system with quality components is a legitimate investment for the right homestead. I'm not telling you to tear your panels down. What I'm telling you is that the off-grid industry, like every industry, has a strong interest in selling you components, in selling you upgrades, in creating complexity that keeps you coming back for parts and service and advice. And in doing so, it has completely buried the fact that for low power, long duration, off-grid applications, particularly in remote locations where running wire is a problem, the Earth itself has been used as a power source for the better part of 2 centuries. Let me give you some numbers to put this in perspective. A single well-constructed copper-zinc earth battery cell, buried correctly in moderately moist loam or clay soil, will produce somewhere between half a volt and 1.5 volts of DC electricity continuously. Stack 4 or 5 of those cells in series, which I'll explain how to do, and you're looking at 3 to 6 volts, enough to power a modest array of LEDs, enough to charge small capacitors, enough to run soil moisture sensors, temperature sensors, remote gate indicators, animal trail cameras on trickle charge, and small radio receivers. Enough to keep a low-draw emergency beacon powered indefinitely in a remote location. Is it going to run your house? No. I'll be straight with you about that because I think you deserve honesty more than you deserve hype. It's not going to run your washing machine. What it is going to do is keep low-power, high-value systems alive with zero ongoing cost and zero maintenance once it's in the ground, and that is genuinely useful. That is genuinely powerful in a practical sense, especially when you think about what those systems do for you. A trail camera that warns you something is in the chicken yard at 3 in the morning. A moisture sensor that tells you when the root zone of your winter squash hits a certain threshold. A small LED beacon that marks your wellhead or your septic access or your root cellar entrance so you can find it at night without burning a flashlight battery. All of that running indefinitely off $39 in hardware and the ground under your feet. The power industry doesn't want you thinking about this. Not because it's dangerous, because it's free. The Earth battery is not a new idea. It is not something I invented or someone on the internet invented. It has a documented, traceable, peer-reviewed history that stretches back to the early 1800s. In 1841, a man named Alexander Bain, a Scottish clockmaker and inventor, received a British patent for a telegraph system that used earth plates instead of traditional chemical batteries for its power source. Bain buried iron and zinc plates in the ground at either end of his telegraph line and used the naturally occurring electrical potential difference between those dissimilar metals, combined with the moist soil acting as an electrolyte, to generate the voltage needed to transmit telegraph signals. This worked. It was documented. It was used operationally. Around the same time, a series of researchers and telegraph engineers in both Europe and North America began experimenting with what were called telluric currents, naturally occurring electrical currents that flow through the Earth's crust. These are real. They've been mapped. They interact with the ionosphere, with geomagnetic fields, and with the electrochemical activity of soil bacteria and mineral gradients. The early telegraph engineers weren't just using a simple galvanic cell when they buried those plates. They were also, to some degree, tapping into these broader earth currents. The science gets complicated there, and I don't want to overclaim, but it's documented that some earth battery installations produced more current than a simple galvanic reaction alone would predict. In 1875, a researcher named Stoney published observations in scientific journals documenting the voltage outputs and current characteristics of buried metal plate systems across different soil types. Clay-rich soils with high moisture retention consistently outperformed sandy or rocky soils. Loam with organic matter did particularly well. which makes sense once you understand the mechanism, and I'll get to that. Throughout the late 1800s and into the early 1900s, earth batteries were used to power telegraph stations in remote locations, to operate simple signaling equipment along railway lines, and in some rural farming communities in Europe, particularly in Germany and Scandinavia, to run basic electrical devices before grid infrastructure reached those areas. So why did this disappear? Two reasons, and they work together. First, the commercial battery, and then the electrical grid arrived. Both were more powerful, more predictable, and could be sold to you repeatedly. An earth battery, once buried, just sits there producing power for free. That's a terrible business model if you're trying to build an electrical utility company. Second, and this is the part that always gets glossed over, the earth battery requires you to understand your soil. It requires you to be a participant in your own electrical generation. The grid doesn't ask anything of you except a mailing address and a credit card number. Commercial batteries don't ask anything of you except that you throw the old one away and buy a new one. The earth battery asks you to dig a hole, understand your soil chemistry at a basic level, and spend an afternoon with some copper sheet and some zinc hardware. That's not complicated, but it creates an independent person, and independent people don't generate recurring revenue. The Amish, who have maintained a deliberate distance from grid dependency for theological and community reasons, have documented variations of earth battery usage in some communities, particularly for powering low-draw farm signaling systems and simple electronic sensors that help them maintain animal welfare monitoring without violating their community standards around grid connection. I've spoken with homesteaders in Pennsylvania and Ohio who have family oral history of these systems going back to grandparents who used them before rural electrification reached their area in the 1930s and 40s. Indigenous land stewards in the Pacific Northwest have traditions of recognizing certain soil zones, particularly near iron-rich mineral deposits and areas of high microbial activity, as areas where the land itself has a certain energy. Modern electrochemistry has a fairly clear explanation for why those observations are accurate, and it maps almost perfectly onto where an earth battery would perform best. This is not magic. It is not mysticism. It is electrochemistry, and it works. Let's talk about what's actually happening underground when you build one of these, because understanding the mechanism is what's going to help you site it correctly and get the most out of it. An earth battery is, at its core, a galvanic cell. If you remember anything from high school chemistry, a galvanic cell is what you get when you put two different metals in contact with an electrolyte solution. The two metals have different electrochemical potentials, meaning they give up electrons at different rates. When you connect them externally through a wire, electrons flow from the metal that gives them up more easily to the metal that holds onto them more tightly. That electron flow is electric current. The most common and most efficient pairing for a soil environment is copper and zinc. Copper has a standard electrode potential of positive 0.34 volts. Zinc sits at negative 0.76 volts. The difference between those two values gives you a theoretical cell voltage of about 1.1 volts. In practice, in real soil conditions, you'll see anywhere from 0.5 to 1.3 volts, depending on your soil moisture, your soil mineral content, your soil temperature, and how much surface area your plates have. The electrolyte in this system is the soil itself. More specifically, it's the soil water, which carries dissolved minerals, salts, organic acids from decomposing matter, and the metabolic byproducts of soil bacteria. This is why organic-rich soil, particularly loam or compost-amended soil, performs so much better than pure sand or rock. The more biologically active and chemically rich your soil water is, the better your electrolyte, and the better your cell performs. Here's something most people don't talk about when they discuss earth batteries, and I think it's the most fascinating part of the whole thing. The soil bacteria aren't just passive bystanders in this process. Certain species of electrochemically active bacteria, particularly from the families Geobacter and Shewanella, are literally transferring electrons through the soil as part of their metabolic process. These bacteria oxidize organic compounds in the soil and transfer the resulting electrons to mineral surfaces, including metal electrodes. This is a real and well-documented phenomenon called extracellular electron transfer. These bacteria are sometimes called electrocygens or exoelectrogens. Researchers studying them have built what are called microbial fuel cells, which are essentially a highly engineered version of what you're building in your garden. The soil around the roots of plants, particularly in the zone called the rhizosphere, where root exudates and microbial activity are highest, is especially rich in these electrochemically active bacteria. This is why burying your earth battery plates near the root zone of established plants, or in compost-heavy soil, isn't just acceptable, it's optimal. Now, one thing I want to address directly because I've seen a lot of misinformation on this. An earth battery does not violate conservation of energy. The energy it produces comes from the oxidation of the zinc plate, which is a real, finite chemical process. The zinc plate is being slowly consumed as it gives up electrons. This is the same thing that happens in every battery you've ever used. The difference is that the rate of consumption in a soil environment with a relatively small currents involved is extremely slow. A zinc plate of reasonable thickness, buried in average soil, might last 5 to 10 years before it requires replacement or supplementation. Copper is essentially stable in this environment and doesn't degrade meaningfully. So, your ongoing cost after the initial setup is periodic zinc replacement, which is a fraction of what you'd spend on commercial batteries over the same period. The telluric current component I mentioned earlier is real, but harder to quantify, and depends heavily on location, depth, and local geology. In locations with iron-rich or mineral-rich subsoil, or near running water, some users report significantly higher outputs than the galvanic cell alone would predict. This is likely a combination of natural ground current concentration and enhanced electrolyte conductivity from dissolved minerals. If you're in an area like this, your results may genuinely exceed what I'm describing as a baseline. Temperature affects output significantly. Cold soil reduces bacterial activity and decreases ion mobility in the soil water, which drops your voltage and current. In northern climates, you'll see your earth battery output drop in winter and rise again in spring. This is expected and normal. It doesn't break the system. It just means earth batteries are a better complement to winter solar than a replacement for it. Moisture is the other big variable. Dry soil is a poor electrolyte. Your earth battery performs best in consistently moist soil. This is why siting near an irrigation zone, near a rain catchment system, or in a naturally low-lying area that retains moisture is a smart move. Some builders install a simple gray water slow drip near their earth battery array to keep the soil moisture consistent through dry seasons. Used dishwater, rinse water, that kind of thing. Organic matter in the water actually improves performance. This is one of those genuinely elegant off-grid integrations where two systems support each other. All right, let's build one. Here is your materials list. Write this down or screenshot it. First, copper sheet, or heavy copper flashing. You want 16 gauge or heavier. Thinner than that, and it's too flimsy to handle well. You're looking at a plate size of roughly 6 inches by 12 inches per cell. Your local roofing supply house or big box hardware store will carry copper flashing in rolls. A 10-foot roll of 6-inch copper flashing runs about $18 to $22. That's enough for multiple cells. Second, zinc. You have a couple of options here. Zinc-coated steel, meaning galvanized sheet metal, works but is not ideal because the zinc layer is thin and degrades faster. Better option is a solid zinc anode, which is sold specifically for marine and underground corrosion protection. These are available at marine supply stores, farm supply stores, and online. A pair of zinc anodes rated for underground use, roughly the same dimensions as your copper plates, will run you $10 to $15 for the pair. Third, heavy gauge insulated copper wire. At least 18 gauge, 12 gauge, if you want to handle higher current builds or longer wire runs. You probably have some of this already. If not, a 25-foot roll of 12 gauge insulated wire from a hardware store is around $5 to $8. Fourth, waterproof wire connectors or marine-grade crimp connectors. Do not use standard wire nuts in a buried application. They will corrode and fail. Get the gel-filled waterproof butt connectors or heat-shrink crimp connectors, $3 or $4. That is your total. Depending on what you already have on hand, you're at $35 to $42 for a complete 4-cell array. If you're comfortable calling it $39, I won't argue. You also need a multimeter to test your output. If you don't already own one, a basic digital multimeter runs $10 to $15 and is one of the most useful tools on a homestead anyway. Get one. Now let's talk about siting. Choose a location where the soil stays consistently moist. A garden bed, near a compost pile, a low area near a rain barrel or a gray water outlet. Avoid areas with heavy root competition from large trees that will dry out the soil zone. Avoid areas with very sandy or gravelly soil. If you have a patch of dark, rich loam or compost-heavy garden soil, that's your best starting point. Soil temperature matters. If you're installing in late fall in a northern climate, your initial readings will be lower than they will be in spring. Don't judge the system by its winter performance. Now for construction of a single cell. Your copper plate is your cathode. Your zinc plate is your anode. These terms matter because they determine which way your current flows and which wire is positive and which is negative. The copper is positive. The zinc is negative. If you ever check with your multimeter and the reading is negative, or you're getting nothing, you've got your leads crossed. Strip about 2 inches of insulation from the end of your wire. Wrap it tightly around one corner of your copper plate and secure it with a stainless steel screw and a stainless steel washer pulled tight against the metal. Do not use galvanized screws here because you'll create a secondary electrochemical reaction at the connection point, stainless only. Do the same with your zinc plate and a separate wire. Now you're going to dig. Your plates need to be buried at a depth where soil moisture is consistent year-round. In most climates, this is somewhere between 12 and 24 inches. Shallower than that, and you'll see significant moisture variation. Deeper than that, and you start losing accessibility for maintenance, and you may get into soil layers that are less biologically active. The copper and zinc plates should be buried roughly 6 to 12 inches apart horizontally in the same general soil zone. They should not touch each other. If they touch, you short the cell and get nothing. The gap between them is the soil acting as your electrolyte. Orient your plates vertically in the soil rather than horizontally. This gives you better surface contact with the soil on both faces of the plate and allows moisture to move past the plate surface more freely. Once your plates are in position, backfill carefully, pressing the soil firmly against both plate surfaces. No air gaps. Air gaps are dead zones where no electrochemical reaction can occur. If your soil is quite dry at installation time, water it thoroughly after backfilling and let it sit overnight before you take your first readings. Run your wires up to the surface at an angle so the wire exits the soil a few inches away from directly above the plate. This reduces moisture migration up the wire and reduces frost heave stress on the connection point. Where the wire exits the soil, seal the entry point with silicone caulk or bury a short section of plastic conduit through the frost layer so the wire is protected from movement. Connect your multimeter to the two surface wires, copper to positive lead and zinc to negative lead. You should see voltage. In good soil with fresh plates, you should see between 0.6 and 1.2 volts on a single cell. Now stack your cells to get usable voltage. 4 cells in series, meaning you connect the copper positive of one cell to the zinc negative of the next, and so on down the chain, will give you somewhere between 2.5 and 5 volts, which is enough to power small LED arrays, most low-draw sensors, and trickle charge applications. Space your buried cells at least 3 feet apart in a row or in a grid pattern. This prevents the soil between adjacent cells from becoming saturated with reaction byproducts and keeps each cell operating in relatively clean electrolyte. Bring your series wires to a central junction point above ground where you can connect to your load. A small weatherproof electrical box from a hardware store, $1 or $2, works fine for this junction. For LED applications, add a simple current-limiting resistor in line with your LED array. A 330 ohm or 470 ohm resistor in series will protect your LEDs from overcurrent as your cell voltage fluctuates. These resistors cost pennies at any electronic supply house and are worth including. For charging applications, a small voltage regulator and a blocking diode to prevent backdrain from your load device back into the earth battery array are worth the extra few dollars. TP4056 based lithium charging modules, which cost around $1 to $2 each from electronic suppliers, can buffer the earth battery output into a small lithium cell, which then provides stable power to your device. This is the most reliable way to run remote sensors or trail cameras off an earth battery array. Do not expect to run high-draw devices directly off your earth battery. The internal resistance of a soil galvanic cell is relatively high, meaning current draw above a few milliamps will cause your voltage to sag significantly. The right way to use these systems is as a slow charge trickle source into a storage cell or capacitor, not as a direct drive power source for anything with significant current demand. Check your output monthly for the first 6 months. Take a reading with your multimeter and log it. You're looking for consistency, and you're watching for gradual decline that might indicate the zinc is depleting faster than expected in your particular soil chemistry. In high acidity soil, particularly near decomposing organic matter, the zinc oxidizes faster. You can slow this by adding a pinch of baking soda to your backfill soil to buffer the pH slightly toward neutral. If your voltage drops significantly after 6 to 12 months, dig up your zinc plate and inspect it. Zinc oxidizes as a white or gray powdery coating. If the plate has thinned substantially, replace it. If it still has material left, you can lightly brush the surface with a stiff wire brush to expose fresh zinc and reinstall it. Your copper plate will look patchy and green from the oxidation process, which is normal and doesn't affect function. Do not try to clean the copper. Leave it alone. Here is what you are actually going to get out of this. You are going to get an earth battery array that costs you less than $40 in an afternoon. You are going to get a system with no moving parts, no maintenance interval shorter than 6 to 12 months, no noise, no fuel, no grid connection, and no monthly bill. You are going to get between 2 and 6 volts of low-current DC electricity that is available continuously, day or night, sun or cloud, wind or still air. You are going to be able to run LED lighting in a remote location on your property, keep a sensor array powered indefinitely in a garden bed, trickle charge a small battery bank to keep a trail camera or radio receiver alive, and mark critical infrastructure points on your homestead with reliable low-draw lighting that doesn't depend on anything except the chemistry of the ground you're standing on. In 1841, Alexander Bain buried some metal plates in the ground and sent telegraph signals across Scotland. In the 1870s, telegraph operators in rural America used earth batteries to keep communications running in locations too remote for conventional battery resupply. In the 20th century, that knowledge was buried along with those plates, not because it stopped working, but because working indefinitely for free doesn't serve any business interest. You now know how it works. You know what to buy. You know how to site it, build it, wire it, and maintain it. $39 an afternoon, a patch of moist soil. The grid is not your only option. It never was. That's the whole point of the unseen farm. The knowledge doesn't disappear just because nobody's selling it to you anymore. It just waits in old patents, old journals, and old family memories until someone decides to dig it up. Get out there and start digging.